Okay, this is part 2 of the lecture on bodeplots. Where lecture 1 finished off was we basically put a transfer function in bodeplot form, meaning we replaced s with j omega, and then we factored out the constant terms in the denominator so that we had everything in the form of j omega over something plus 1 and a gain in the numerator. So we did this algebraic manipulation so that we could get the transfer function to look like this, because this is going to tell us something about how to manipulate the transfer function. Okay, so what we want to do next is we want to take the magnitude of the function and then we want to convert it to dB. So here is our function that we finished up on the previous page. Let me grab a pen here. Here's our function that we ended up with on the previous page right here. And so what we want to do is we want to work with this. So here it is, just repeated here on this line. And we're going to take the magnitude of h, which means we're going to take the magnitude of each term. So I've done that there. And because these terms are multiplied together, they're already factored, then you can just take the magnitude term by term, and it basically ends up giving you the same result as if you multiplied everything out and took the magnitude of the whole thing. So the product of the magnitudes is the same as the magnitude of the products. So now we want to take the log. We want to take 20 times the log of h. So I want to point out that we could actually stop right here, calculate an exact magnitude using our complex number math and taking the square root of the real part squared plus the imaginary part squared for each term. We could get an exact amplitude of h that would be the ratio of numerator to denominator. But we want to take the log, and the reason we want to take the log is threefold. First of all, taking the log makes us able to view functions that change over orders of magnitude on one single page, or on one single graph. So it makes it look more linear when we graph it. If it has, and here obviously we have a cutoff frequency at 10, we have one at 100. If we plot that on a log scale, we'll be able to see more clearly the behavior across orders of magnitude. Secondly, when we take the log allows us to take things that are products and division and change it to addition and multiplication by property of the logarithm. So that's going to make it really convenient to treat this term by term. And then finally, taking 20 times the log puts our units in dB, which is a common unit that's used in electrical engineering as well as acoustics. So if I take the log of this entire term, what I basically have in the numerator is I have the product of two terms. And we need to remember that the property of the logarithm, the log of a times b, is the log of a plus the log of b. And then in the denominator, I have two additional terms. And so since the numerator since these two terms are in the numerator, then what's going to happen is the log of a over b is the log of a minus the log of b. So basically, terms in the numerator that are multiplied together end up adding, terms in the denominator end up subtracting. So from this expression, we're going to end up with four terms. First, we will have 20 times the log of 1 over 1,000. That comes from right here. Then we'll have 20 times the log of the absolute value of j omega. That comes from right here. Then we have minus 20 times the log of j omega over 10 plus 1. That's this term in the denominator with the property of the logarithm, division property of logarithms applied. And then finally, we have this last term in the denominator, j omega over 1,000 plus 1, that's shown here in term 4. So it's minus 20 times the log of that term. Now, what we want to do in this lecture is go through term by term and look at what each one of these is actually saying. So if we look at term 1, it's 20 times the log of 1 over 1,000. And remember, what's the goal here? We're trying to determine the magnitude of this transfer function as it changes or as a function of omega. So we want to know what happens for each term because the terms are added. So if I could get a graph for each term, then I could add all the graphs even visually, and I'd have basically a result. So if I start with 20 log of 1 over 1,000, this is just a constant. There's no omega here. So when I take the log of 1 over 1,000, I'll get minus 3, and then when I multiply that by 20, I'll get minus 60 dB. Basically, this is just a constant that determines the vertical positioning of the graph. So instead of 1 over 1,000, this were 1,000, this number would be 60 dB. So basically, we're going to take our final plot and add or subtract this constant gain to every point on the plot, and that's going to have the effect of shifting the bodeplot curve up and down vertically depending on its value. And this is constant across all frequencies, so it's just going to take your bodeplot curve and move it up and down. Okay, term 2, 20 log times the absolute value of j omega. So when we take the absolute value of j omega, we get omega. Now this is just going to be a straight line with log of omega. So I've printed out some values here. When omega is 0.01, 20 times the log of omega is minus 40. When it's 0.1, 20 times the log of omega is minus 20, and so on. So what this really plots out to be, if I look over here and I plot it, and what I've done is I've plotted this on a semi-log scale here. So the horizontal axis represents 0.01, 0.1, 1, 10, 100, 1000. So it's ticked off even tick marks in orders of magnitude. And then the vertical axis is just plotting dB. So you can see that for this term, what we're getting is we're getting a straight line. And notice that it never flattens out. It's straight from negative infinity to positive infinity. So for this term only, this is the kind of graph that I would get. Now let's look at term 3. Term 3 is a little more complicated. Basically, term 3 is this minus 20 times the log of the absolute value of j omega over 10 plus 1. So in this case, first of all, what we're going to do long term when we actually plot bodeplots by hand is we're going to make some approximations. So this changes depending on the range of frequency you look at. If omega is very small, and very small is defined as this term in the denominator. So right here is the reason that you want to write this in bodeplot form, because you cannot easily identify where the breakpoint in behavior is. So if omega is much, much less than 10, then this imaginary part of this number is a very small fraction. And we basically have this whole thing approximately equal to minus 20 times the log of 1, which is 0. So as you trend smaller or lower in frequency below 10, you're more and more going to approach a constant value of 0. Now if we let omega get large, so omega is going to become much, much greater than 10 in this second line. When that happens, the first number is a lot larger than the second number in this absolute value sign, so we can ignore the 1. So we'll basically have minus 20 times the log of the absolute value of j omega over 10. The absolute value of j omega is omega. The absolute value of 10 is 10. So we once again have a division. So we can then take minus 20 log omega minus a minus 20 log of 10. Okay, if you just kind of look at this and remember this is only applicable for when omega is much, much greater than 10. So for example, if omega were 100, we would have minus 20 times the log of 100, which is minus 40, plus 20 times the log of 10, which is plus 20. So we would have approximately minus 20 dB. And so you can plug in values here to get an approximation. Now what I've done in this table below is I've actually taken the original expression right here, and I've basically used the formula for the magnitude. So remember, the magnitude is the square root of the real part squared plus the imaginary part squared. So real part squared plus imaginary part squared, square root. So if you do that, and then you take the log of whatever you get, and you multiply that by minus 20, you've actually created an exact value. So shown in this table here, I just basically did a little Laplace spreadsheet, and I calculated the exact value given omega the exact value of what this minus 20 log of this expression would be. And then I plotted it. So here's what the magnitude of h looks like if you basically plot a smooth curve between these exact values. And once again, we did that on a log scale. So notice here that the value of this curve is 0 until you get close to this value of 10. Right at 10, it's not obvious here on this graph, but right at 10, you're at a minus 3 dB point. And then basically you enter this slope region where you're decreasing by 20 dB per decade. So at 100, you're down minus 20. At 1000, you're down minus 40. And notice the farther you get from this break point of 10, the closer you are to the approximation that you would be at minus 20, minus 40, minus 60, and so on. That is because the curvy curve is approaching the asymptote. Same thing is happening on the lower frequency end, where when we approach, as we get smaller and smaller, we get closer and closer to a constant value of 0. But terms like this, where you have a j omega term plus 1, these terms are going to have a shift in behavior at whatever this term is and whatever this value is in the denominator. So at 10, we're going to have what we call a break point. Okay, so let's go back and look at our previous behavior of our first term. We had a positive slope here. If I were to take this curve and I were to add it to this curve, up to 10, I'm basically adding 0. So this is going to continue just like it was. At 10, the curve that I'm adding to this red curve is going to have a negative slope. The negative slope and the positive slope, when added together, will cancel each other out and give you a constant value, or a constant value approximately. So what our asymptote's going to do is the low frequency behavior is going to have this plus 20 dB per decade slope. At 10, that's going to flatten out and give you 0 slope. Now, in this particular example, we had a third term. The third term has another breakpoint at 1000. And at 1000, we're going to pick up the same kind of behavior that we picked up from the previous term, just at a different location. So the previous term had a flat slope to 10 and then a negative 20 dB per decade. This term will have a flat slope up to 1000 on the asymptote and then a negative 20 dB per decade. So what that means is this term does not contribute to the overall sum because its value is 0 until you get close to 1000. This term doesn't contribute to the overall sum until you get close to 10. So at 10, you pick up this negative 20 dB per decade slope, which cancels this positive 20 dB per decade slope, giving you a net slope of 0. As you now get close to 1000, you pick up another negative 20 dB per decade slope. So when this one is added to this one and this one, which are giving you 0, then you have a net minus 20 dB. So let's go back from the previous lecture and look at the MATLAB plot of this function. Well, looks like maybe I don't have the MATLAB plot handy. I can pull that off of MATLAB. Let me end my show. And let's go to MATLAB. Here's that plot. So here is that early low frequency behavior that is governed by term 2. It's your 20 dB per decade slope. When you reach this omega equals 10 value, you pick up a negative 20 dB per decade slope, but this one is still there. So remember, coming back here, this term is contributing this positive slope from the lowest possible frequency to the highest possible frequency. So that's always going to be present. So now what's happened is we've picked up a second term because that denominator term is beginning to impact, and that has flattened out the slope of the numerator. And then finally, when we get to 1,000, we pick up another term in the denominator that adds another negative 20 dB per decade, resulting in a net slope of minus 20 dB per decade. So that's how this curve is traced out. Now you notice the maximum value is at minus 40. So basically, if I come down here to omega equals 1, and I sort of draw a vertical line, you notice that I get very close to minus 60 dB. So what is minus 60 dB? Minus 60 dB was the value of our DC gain term. So to get the vertical positioning of the Bode plot, come to omega equals 1 and come up to that low frequency asymptote. That point should be your gain. Why? Let's come back and look at this series of terms again. What happens if I plug 1 in for omega here? I basically have 20 times the log of 1, which is 0. If I plug 1 in here, I have 20 times the log of just barely over 1, which is very close to 0. If I plug it in the fourth term, I have 20 minus 20 times the log of 1 plus something over 1,000, which is 1 over 1,000, which is also very close to 1. So I'm basically at omega equals 1. All of these other terms effectively contribute 0. The only time that's not the case is if one of these breakpoints or one of these critical points occurs at a value less than 1. In that case, you have to make a special adjustment in how you do the plot that we'll discuss later. So anyway, this is the theory behind how Bode plots are done. Now, is this what you're going to do every time you do a Bode plot? No, it's not. What you're really going to do is you're going to do some shortcuts. And the shortcuts are very easy to do. They can basically be read from a transfer function directly without really even substituting in j omega. But it's important to understand that the reason that works is that basically, theoretically, what you're doing on this magnitude plot is you're substituting j omega, you're taking the absolute value, you're taking 20 times the log, you're expanding out each term, and then you're calculating an asymptotic type plot or determining an asymptotic type plot for each type of term. So now what we're going to do next is we're going to learn how specific forms or specific types of terms will contribute to a Bode plot. And so you can actually group them into certain types of contributions. Once you figure that out, then you don't have to ever go through this whole rigmarole again of the substitution of j omega. But it's very important to see this once so that you know exactly what's going on.